Good evening, everyone. My name is Douglas Sprang, and I lead the Energy and Environment series for the MIT Club of Northern California. I'm delighted to kick off our fifth event of the 2022-23 season, which has featured top speakers in the fields of renewable energy, and which I believe includes nuclear, electric vehicles, hydrogen, and climate change. Our speaker this evening is MIT professor Michael Short. His topic is debunking the myths of nuclear fission. He will address the issues that have caused decommissioning of or slowed down the building of new nuclear power plants, depriving the industry of providing more baseload power to balance the mix of intermittent and non-intermittent power generation. Safety and waste disposal are at the top of the list, but the cost of huge nuclear power plants and delays in the permitting and regulatory processes are other major inhibitors. Mike will tell you all about this and more tonight. By the way, the registrations as of a few minutes ago were 315 for this event, and that's the second highest we've had in the 3 years of putting on these virtual events for energy and environment. So we're really excited about the tremendous support of this event. We have enabled live Q&A, and I'll do my best to get some of those questions to our moderator to add to many of the questions we got from online registration. But because of the very large audience, we won't be able to get to all of them. By the way, you may want to, if you're not already, viewing this event in gallery mode on Zoom. And by doing that, when you have two speakers, they'll be side by side as if they're doing a fireside chat. And it's just a better format in general, I think, for viewing. With that, it's time for our program to begin. So I'll be back at the end to close things out, but now I'd like to introduce our moderator, Larry Kelly, a long-term contributor to our series, and an alum, MIT alum, with a degree in nuclear science and engineering, who will orchestrate tonight's fireside chat. So take it away, Larry.
Doug, thanks very much. 315, boy, that's just fabulous. So it is my considerable honor to introduce Mike Short to our audience tonight. Mike, you can turn on your video. There you are. Mike, it is always good to see you. Just wonderful. So Professor Michael Short is the Associate Director of the Plasma Science and Fusion Center at MIT, and is the class of 1942 Associate Professor of Nuclear Science and Engineering. Mike is a local boy, having grown up in Swampscott. He started coming to MIT on Saturdays in high school as part of the educational studies program that MIT puts on. In this program, MIT students taught high school students what Mike calls the wackiest courses, things that you couldn't get in high school, such as combinatorics, Chinese, genetic engineering, exothermic chemistry, that is to say the chemistry of explosives, and others. And this is when Mike knew that MIT was for him. So Mike, was it the explosives?
It was certainly a factor, yeah.
Like many of us, he started in course 6, and in his freshman year, he did a year up in course 22 under Ron Ballinger on corrosion testing. Energy was so exciting and nuclear was so enticing that Mike switched out of EE and into nuclear. He says that there are two big issues in nuclear: politics and materials, with materials being the larger issue and the one where he could have significant impact. Both fission and fusion have materials challenges. After undergrad, Mike flirted with a few startup opportunities and decided that the fake it till you make it routine was not that attractive. So he returned to the Institute and received his doctorate in less than 4 years. Wouldn't we all wish that we could do that, to get our doctorate in less than 4 years? One of the areas that Mike's work at the Institute has centered on is radiation damage. Almost no one understands radiation damage. And somewhat like Tolstoy's families, each material exhibits radiation damage and is unhappy in its own way. From his work on the basic science underpinning how radiation damage changes materials, Mike developed methods to directly measure said damage. Among his group's surprising discoveries are total radiation, that radiation can make corrosion slower, that energy is stored in the lattice defects caused by the radiation, that there are ways to harvest and measure this excess energy, and very importantly, that there are techniques for detecting uranium enrichment for non-proliferation treaty verification. When Mike's not working on materials, his hobbies include running 20 to 30 miles per week, bike touring, and fixing old and discarded electronics like smartphones. So let me turn it over to you, Mike, and to our audience once again. Please hoot and holler to put your questions in the QA box, and we'll try to get them at the end. It's all yours, Mike.
Thanks, Larry. Thanks, Doug. Thanks, Teddy. And thanks, everyone, for coming. Delighted to be here with y'all. Today, I'm actually going to take you back to MIT a little bit into the course I teach, which is 2201. And for those who weren't in course 22, it's like Nuclear 101. So it's the nuclear equivalent of Unified for Aero Astro, or at the time, some of you might have been there, 6001 or 6002 for ECS. And I'll be talking, I will get to some of the problems I think that are holding nuclear back, the non-materials problems, some of the reasons why it's been so hard to get nuclear going in this country, which are actually some of the reasons it's easier to get it going in some other countries. But I'm going to make sure that we're all in common context first. So because I know there are so few course 22s, Larry, I'm delighted to hear that you're one of them, because I see brass rats in airports and all over the world all the time, but to meet another course 22 alum is a real rarity. It's almost as rare as meeting someone from Boston at MIT, someone who was born here. For some reason, we don't seem to be able to make it the kind of folks that get to stick around. So I'm delighted to be both of those. So to start off today's talk, I wanted to bring you back to the Institute. Imagine you're a second year first semester. You've just taken the GIRs, the General Institute requirements. So you've taken single and multivariate calculus, basic physics, a little bit of chemistry, and I'm not assuming anything else. I am delighted that this is an audience of MIT alums. So if I show an equation or, God forbid, an integral, I know I'm not going to get any, oh, geez, I haven't seen that since this and that. It's excitement I'm expecting rather than shock on whatever other people see when they see math. I don't understand. So it's great to be talking to y'all. So I wanted to get into debunking some of the myths of fission with the material from 2201. So I'll be showing you some actual things from the problem sets that I give my students in class in order to quantify and challenge their assumptions and start getting at some of the core issues that have been making nuclear more difficult to sell, especially in the US. Because what I'm going to put out there is that the hard stuff's easy and the easy stuff's hard. The technical things that I've dedicated my life to, nuclear materials, radiation damage, well, that's the easy part. Because we all agree that science is science and it's worth studying a whole bunch of stuff. The harder parts are the things that aren't as easy to quantify. They're the emotions, the feelings, the politics, the experience, the tragedies convolved with everything else technical. It's the, let's say, the personal side of nuclear, that you can't just logic your way out of an argument with someone and say, oh, gee, I never thought of it that way, because that's not how it works. So what I am going to walk you through is a few places where, if you're interested in quantifying or debunking some of the myths going out there, I'll give you the tools and quantitative things that you need to help debunk those myths. If you're on the fence about whether or not to support nuclear, I'm not going to try to sway you one way or the other, but I will try and present you with a framework for looking at objective facts and peer-reviewed evidence, multiple bits of peer-reviewed evidence. And finally, get at what I think some of the roots of the problems, where some people are arguing successfully about the wrong things when it comes to should we or should we not have nuclear in the world. And so I'll address that stuff head on and leave plenty of room to take your questions about nuclear waste, about radiation, about the cost of nuclear, about fission versus fusion, and anything else that you'd like to discuss. So with that, let's take a step back to 2201. So all the myths that I'm going to be presenting follow the same abstract framework. We've heard lots of these. There's some binary provocative statement about nuclear. It's usually negative. Sometimes if it's coming from the real fanboys and fangirls of nuclear, it might be extremely positive. And the truth in an abstract form for every one of these is going to say, depends how much. You got to quantify things. You got to understand the units so that you're answering and arguing about the same question. And so I'm going to make sure that with nothing but 1801 and 1802, we all GIRs that all of us took, and a little bit of knowledge that I'll teach from 2201, you'll be equipped to explain these to other people too. And so I'm interested to know from the audience, how many of your MIT classes tended to look like this? Feel free to shout out in the Q&A or thumbs up or whatever you'd like. Because when I took things, oh boy, here come the hands. Yep, all right, so sounds like I'm in good company. When I took 2201 in 2002, this is approximately what things looked like. It was lectures, Blackboard, listening, not so much interaction. I had a particularly good instructor, I would say. And even so, this was the old way of teaching things. It's just what everybody did. And I think this is one of the reasons that nuclear has been such a hard sell. It's been largely inaccessible. You need a lot of math and physics in order to understand it. It was taught often in a lecture format. Most colleges don't have nuclear programs. Most high schools don't mention the word nuclear in their curriculum. So this right here, I'm going to put forth that education is actually the root cause of why nuclear is so difficult in this country. I had the opportunity actually last week to have dinner with a few members of Congress who I found to be remarkably good listeners and interested in learning more and interested in how do they sell this story to their constituents. Because, it's interesting. We had don't know if this is a political statement or not, but we got 7 Republicans, no Democrats show up for a dinner on nuclear. And I was amazed at the intensity and honesty with which they were listening and asking questions. One of them happened to be an MIT alum. Made a device to move his chickens around the farm, which he likes to call the Klux capacitor. So search around for that person, you may just find him. I found that to be awesome. Well, now when I revamped 2201, it looks a little different. I'm interested in people exploring nuclear through the lens of their own experiments, their own lives, and sometimes their own bodies, and wanted to walk you through some of the things that we do. For example, you may have heard the idea that there's radiation in bananas, and that's true. Bananas contain potassium. Potassium is about 0.011% potassium-40, and that's a naturally radioactive isotope of potassium. It's been here since the Earth was formed. And so in order to get our students to figure out and calculate how radioactive bananas are, I decided to give them some. Because it's awfully hard to measure the radiation from one banana, I bought 1,000. And through a series of unfortunate jokes, got banned from the Star Market that used to be near Albany Street. So I gave each student about 50 pounds of bananas, had them take them back to the dorms, peel them, and burn them. So the entire campus smelled like banana bread and only the nukes knew why. And we took the ashes and crammed them into a gamma spectrometer to measure the radioactivity of these 1,000 bananas. In terms of exploring radiation through the lens of their own experimentation, we take 25 first years, and on day 1, we have them solder up and test and make a working Geiger counter and look for hidden sources of radiation. And I should mention, these folks are fresh out of high school. So a lot of them don't even know how to solder, let alone anything about nuclear. But we give them these Geiger counters to start exploring the world around them. And I actually have a problem set and a prize for finding the most radioactive place in Boston. Later on, I may pop the question back to you guys and say, what do you think is the most radioactive publicly accessible place in Boston? Even during the pandemic, we made hundreds of these kits and shipped them out to not just our students, but anyone that wanted them, so that they could explore nuclear through the lens of their own self-done experimentation. We even take pieces of our students, for example, toenail clippings that they give, and we throw them in the nuclear reactor, where they absorb neutrons, become radioactive, and through emission of high-energy photons called gamma rays, they tell us what elements are in those toenails. And I'm going to show you one of these because we'll be looking at a couple of these gamma spectra to get us all up to speed on quantifying radiation. And just to point out what you're seeing here, the x-axis is gamma ray energy. The y-axis is a log scale of counts. And yes, we did find arsenic and we did find uranium in some of our students' toenails in absolutely naturally occurring levels. So this whole idea of quantification and understanding that there's radiation everywhere and that it's naturally occurring in addition to the man-made stuff. This to me is one of the biggest reasons why nuclear is such a hard sell. We've had a few accidents in human history They have been spectacular failures. They really sit hard on the human psyche. They've led to a lot of the politics and the regulation behind nuclear plants today. And it's this highly, highly regulated environment that is what makes nuclear so difficult. I'm not saying it shouldn't be there because nuclear plants have to be safe. But we do have to ask ourselves the question, how much regulation are we imposing on ourselves that helps versus success? And what is that doing to dent our fight against climate change? I don't have a quantitative answer to that question, but it is something I want to put out there. We also explore, I'd be remiss if I didn't mention anything about fusion, since as Larry said, I'm the Associate Director of the Plasma Science and Fusion Center. We do let students make their own electrostatic fusers, and shown here is a student making a nitrogen plasma after about a 2-hour workshop. And so these are the sorts of things that all of our students are doing, not just the nukes, but anyone that's got a passing interest. We rope them into our labs. If you want a nuclear UROP, the rule is you're hired, no experience required. We want this to be people's first experience in the lab, and it tends to hook people. So this is, to me, the solution to the problem behind nuclear. I know we're only 5 minutes into the talk, and I'm already cutting to the punchline. It's to build human capital, build the workforce, and get people interested in exploring it at their own pace through their own lens, rather than just listening to whatever they've been told. Speaking about whatever they've been told, let's get to some of the myths. One of the most common myths I hear is all radiation is always dangerous. And despite the fact that it's a myth, it's in US law. There's a rule called the linear no threshold model of radiation dose that says that all radiation is harmful, it increases your risk of death and cancer, and that it's linearly proportionate to the dose that you get. And another myth is that radiation that damages us only comes from nuclear power plants and radiation medical procedures in dangerous amounts. So I wanted to explore whether or not these myths are true through a couple of problem sets from 2201. I'm not going to ask you to do any math, and I will keep equations to a minimum, but since this is an MIT audience, I'm not going to shy away. So to answer this question, we need to learn how to quantify radiation and radioactivity. So to start off with this, rather than start with a definition, we started off with an experiment. A colleague and I bought some honey from Chernobyl. So this is Zona Bluchenia, so the radiation zone in Chernobyl. It used to be that before Chernobyl, honey was one of the biggest exports of that region, and there's a lot of beekeepers there. And so to challenge our students' assumptions, we actually got 2 kilos of honey from the Chernobyl radiation exclusion zone to see whether or not we could measure the levels and whether or not they were dangerous. So we're going to walk you through measuring the radiation in this Chernobyl honey and comparing it to the radiation that you all give off on your own. So these are what the gamma spectra look like. On the top is a background spectrum, which means this is an empty detector, and it's picking up cosmic rays, radiation from the environment, radiation from the building materials, and radiation from the experimenters in the room. And at the bottom, this was the detector full of Chernobyl honey. So the spectrum here is background plus whatever's in the Chernobyl honey. Does anybody see a difference here? If not, you're not alone, because most of my students didn't see any differences either. But when you take these 2 spectra and you slap them on top of each other, there is one little peak right here. That happens to correspond to a 661 keV gamma ray that corresponds to cesium-137, one of the longer-lived radionuclides released during Chernobyl. So in black is background, and in red is the Chernobyl honey spectrum with that little difference right there. And we're going to focus on that to quantify how radioactive is the honey coming out of Chernobyl. To do that, we're going to use a small equation that we developed in class that I'm going to walk you through right now. This is an equation to quantify radioactivity of something based on one of these gamma spectrum counts. So it goes from an experimental measurement of counts over a certain amount of time, like how many gamma rays the detector absorbed, takes into account some fundamental nuclear data, and outputs radioactivity in a unit called becquerels, or BQ. This is the number of radiation decays per second. So when each atom decays, it gives off, in this case, a beta particle, a lone electron, and a gamma ray, or a high energy photon that we measure. To go into this equation, we need to know the honey count rate, the number of counts per second in that little red peak. The background count rate, if there were a peak here, we would have to subtract it. Luckily, there's not. There's just some noise, so we don't have to worry about that. The likelihood of photon emission per radioactive decay, which is not 100%. Something about the efficiency of our detector at capturing these gamma rays, and what's called the branching ratio, the likelihood of this type of radioactive decay per becquerel or per radiation decay. So I pre-looked up the nuclear data tables for cesium-137, and a couple of the values that we're looking for are right here. If we look at this gamma ray energy at 661 keV, we get our gamma efficiency. About 85.1% of the disintegrations result in a gamma that we measure. We also see that the branching ratio is 1 right up here, so that makes it easy. And because there's no peak in black corresponding to the red, the background counts of cesium are 0. That's good news because that means that my lab is not contaminated with radioactive cesium. So awesome. All we now need to do is numerically integrate the area under this tiny little peak and divide by the amount of time in seconds that we were counting for. We got about 206.1 counts in 86,400 seconds, or 1 day. And we arrive at a radioactivity of this sample, 0.7 becquerels. So this bit of honey is giving off a little less than 1 radiation disintegration per second from the radioactive cesium left over from Chernobyl. We now have to divide by the 2 kilos of honey to get specific activity in becquerels per kilogram. This is an important step because it makes sure that we're looking at the radioactivity of a substance independent of how much substance there is. And this is the origin of a lot of the myths you'll hear about nuclear. You might hear, oh, well, this or that accident released this much radioactivity, or you're giving off 500 million disintegrations per second of this or that isotope. Normalizing it to some comparable quantity is the difference between getting scared and getting educated. So when we divide our 0.7 becquerels by our 2 kilos of honey, we get a specific activity of 0.35 becquerels per kilogram of Chernobyl cesium. That's very measurable, right? We were able to measure it with quite a high certainty. It's not that high of a dose, but I would not take my word for it. Let's do another calculation to prove it. So now I'm going to ask, how much radiation do you give off compared to honey from Chernobyl or bananas or whatever? Because you're giving off radiation right now. You also contain potassium, carbon-14, radium, all sorts of other isotopes that are naturally occurring on Earth. And in order to convince our students to do this calculation, I give them my favorite problem set of the year, which happens to be the last one. Calculate the dose you get from spooning. My favorite problems to give at MIT, they're one question, one sentence for me to ask, and about 7 pages of math to solve. So I asked my student, if you were to do what these dogs are doing, compared to sleeping alone, how much more radiation dose would you absorb? So like any good problem, those of you who are in 801 and you may have been asked to calculate the volume of a cow, the answer is usually, well, let's start by assuming a spherical cow. So let's assume a prismatic dog or 2. We'll model these 2 dogs as slabs next to each other with some specific radioactivity to them, some amount of radiation per mass. We cut them into infinitesimally thin slices with some thickness dx. And we note that each little slice of dog is giving off radiation in all directions. We'll make a simplification that the dogs are much taller than they are thick. So we'll simplify this to a one-dimensional problem. And we'll note that some of the radiation this slice of dog gives off is absorbed on its way out of the first dog. Some of the radiation will go flying through the other dog and out the other side. So it's like it wasn't absorbed. And we're after the amount of gammas that each slice of dog 1 emits and are absorbed by dog 2. This is going to say how much we radiate each other. So let's now reduce this to a bit of math. I'm not going to walk you through all the bits and pieces, but I will say we've taken each of those English terms to find a symbol for it. Now we have to come up with mathematical expressions to model the amount of radiation coming from each slice. We put those into an integral where we'll arrive at a rate of gamma absorption. And then I'm going to skip all the math here, but I'm not going to hide it from you. Just so you know, another thing that we don't do at MIT anymore is we don't skip steps. I don't know how many of you were in a class when I said, well, somebody said, well, it's intuitively obvious that the result of this integral is this. That really frustrated me when my professors did that. So I don't like to skip steps anymore. I don't want to assume anything. But if we get all the way to the end, we arrive at a gamma absorption rate of 115.6 gammas per second from spending the night next to someone. So let's go back to our Chernobyl honey. We know that there are this many gamma rays per kilogram of honey leaving the honey. If you were to eat the honey, let's make a conservative assumption that you would absorb 100% of the gammas, even though some of them will escape from you. They will not interact with the matter in your body and make it out. But let's be conservative. Let's call that then 0.35 gammas per kilo per second absorbed from Chernobyl honey. So let's save that value and take our spooning dogs example and the end result of 115 gammas per second, divide by my weight, 78 kilos of professor, and you get that I would irradiate somebody about 4 times as much if I were to spend the night next to them, as opposed to eating 2 kilograms of honey. And if I ate 2 kilograms of honey, radiation would be the least of my concerns. I think I'd be a little sick to my stomach or possibly explode my pancreas. So there you go. Things do emit radiation. But the difference is radiation is not always dangerous. The real answer is too much radiation is dangerous. There are levels which are safe. There are levels which don't cause any ill effects to within the knowledge of our statistics and uncertainty. I can't say for sure that the linear no threshold model is wrong, but there is not sufficient evidence to say that it's right. In fact, we do the math for this in my class too. Given the uncertainty of knowing how much radiation is harmful, you would have to expose about 60 million people to small amounts of radiation to tell whether or not it's harmful. Good luck getting that past any ethics board, let alone finding 60 million volunteers willing to get lightly irradiated. And the other myth that radiation only comes from nuclear power and medicine, well, we know that radiation comes from space. We've measured that it comes from our food, and we've calculated that it comes from us. In fact, there's another crazy myth going around that this one's hot off the press. Didn't even have time to do the math on this. It's been floating around and says that if there's 100 million people in one space, they would all irradiate each other to death. And if you go back to this calculation and you figure each person is giving off this many gamma rays per second, and you stop there, okay, maybe that sounds plausible, right? This times 100 million is a whole lot of gamma rays. Luckily, most of these people occupy some volume. 100 million people would take up an enormous amount of volume. Most of them would shield the others from their gamma rays. And the only way in order to get to that level of 100 million people's worth of radiation in one spot would be to compress them into a singularity, as in throw them into a black hole. We can't do that, and I wouldn't want to do it if we could. So that's a myth because of a lack of system thinking. They've taken a number like this, they've multiplied it by 100 million people and said, whoa, that's a dangerous amount of radiation. And they're right, it's a dangerous amount of radiation. They neglected the fact that people take up volume. And so there is radiation all over the place. I wanted to show you an example. If everyone looks up in their house, you may happen to see a smoke detector. Well, I've taken the sources out of 16 of these smoke detectors, which look like those little discs. We sprinkled some zinc sulfide on them. And after letting the camera adjust and get to an ISO 400,000 exposure, they start to glow. What you're seeing here are the photons being released from scintillation from individual alpha particles in those smoke detector sources. So you're actually visualizing pretty close to individual radiation decays with an incredibly sensitive camera from a consumer appliance, something you can buy at Walmart. And that radiation, because of the form it's in and charged particles, doesn't make it out the smoke detector. So not all radiation is dangerous. It depends on if you ingest it or not. It depends on how much. It depends on the level of uncertainty and precision to which we can quantify ill effects from radiation. And it would take a rather unethical medical board in order to allow an experiment for us to find that information for real. So I think this would be a great time to take a little break and take your questions about radiation. So in this talk, I'm not going to just talk at you for 45 minutes. I'm interested in talking with you. So feel free to put questions in the Q&A, or Larry, if you'd like to feed me some that you're seeing. Let's answer your most burning questions about radiation.
I'm not seeing, Mike, I'm not seeing any come up in the Q&A yet. Maybe
Okay.
maybe we can talk about safety and waste storage. Would you want to,
Oh yeah, we'll get there pretty soon. So I've got a whole section on waste.
would you rather hold on that? Okay.
Yeah, okay, we can keep going if let's see. Oh yeah, we do actually have a couple more.
Yeah, so some just popped up, right?
Yeah, so I see one from Mather. Can I talk about hormesis? Sure. So for those who don't know the word, hormesis is the idea that a little bit of a bad thing can be a good thing. And it applies with a lot of things that we know about. It works with vitamins. For example, you can get vitamin A toxicity from eating polar bear seal liver because it's just too much. But you need a little bit of vitamin A in order to keep bodily functions going. Radiation has been proposed to be the same thing. Since all life evolved in a radioactive environment because there was cosmic rays and things coming out. And so it's been proposed that without that little bit of radiation, we don't exercise our genetic repair machinery. There have been some interesting experiments where folks have taken rats and put them in either shielded or unshielded boxes, controlled their diets, used rats from the same genome, etc. And the ones from the shielded boxes didn't tend to live as long. They had a little bit more of a early death rate. And that is a low statistical significance bit of evidence for hormesis. We do through all sorts of other studies in 2201 showing hormetic effects. For example, there have been some studies showing that increased exposure to radon up to a very small amount decreases your risk of lung cancer. You wouldn't think so. You would think radon goes in, enters your lungs, cancer happens. There is some credence to this sort of multicellular response where some cells respond to deaths of others by activating repair mechanisms. And so if anybody wants to see those studies, we have them posted in the open courseware link for 2201. So if you go to ocw.mit.edu and search for 2201, you can see some of those studies. I see one from Will Herbert on how much radiation would you get on a trip to Mars, and one from Bert Forbes about high altitude flying. So Will, I don't know the answer to the Mars one. It's something that we could calculate, but I don't have the numbers offhand. But for high altitude flying, you actually get a decent amount. And it's interesting, when the Fukushima disaster happened, and I will address Fukushima in this talk, I had a friend call me from Tokyo and say, should I move back to the US to get away from the radiation? And so we looked up the excess level of radiation due to the Fukushima accident, which was measurable, but in Tokyo it wasn't that high. And we sent them to the FAA, the Federal Aviation Administration's flight calculator, and calculated that they would get a lot more radiation, on the order of 40 microsieverts or so, more than they would by staying in Tokyo. So I said, if you really want to minimize your radiation risk, don't get on the plane. At the same time, there's no real radiation risk from getting on the plane. We're talking about such fantastically small levels in both cases that there was no real danger. To the folks living very close to Fukushima, there absolutely was and continues to be a real danger. The question is how much. So let's see, Jan asked, don't we have some of the data regarding risk of dose related to X-rays? We absolutely do. X-rays are forms of ionizing radiation, and all the data that I've been referring to, X-rays applies to this. And in 2201, we actually cover going from X-ray energy absorbed to excess risk. And so I would refer you there to the open courseware site for how to do that. Lee asked, is it correct that not all radiation is the same? Some energies and particles are more dangerous than others. Yes, you're right. To get back to Jan's question, X-rays and photons are some of the least dangerous bits of radiation there are. And the key variable that we uncovered in class is the more spread out that dose is as the radiation travels through your body, the less damaging it is for the same amount of energy. So to get into Peter's question about how does the energy of the radiation factor into safety, it's not just the energy, although more radiation energy can lead to more damage. But in the case of charged particles, it can actually lead to less, because faster charged particles are moving faster through media and interact less with the electrons causing damage. So I think that gets at Jan's, Lee's, and Peter's problem as questions. So let's see. Oh yeah, so Joe asks, is the highest radiation source in Boston, Cambridge, the MIT reactor? Definitely. Though I did ask the students to find the most radioactive publicly accessible place. Anybody have any idea where that might be? I don't see it in the Q&A. Well, the answer is the hospital. Since there's so many medical procedures going on that involve radioisotopes for tagging or treating things, patients coming out of there can be fairly toasty. And in fact, if you've had a radiation medical procedure, you should tell TSA before getting on the plane because you don't want to surprise them. So Heil asks, how about the length of exposure per day? Is it cumulative? It absolutely is. Though there is a difference between acute, which means very short term, and cumulative or slow term damage. And it turns out that acute damage, if you spread out, if you have a lot of damage at once, it can be very damaging. And if you have a lot of dose over a longer amount of time, to get at Bruce's question, our bodies do heal themselves slowly from radiation. We do have the ability to, let's say, break double diamine bridges in DNA, repair some transcription errors, but not all of them. And it's those errors caused by free radicals in our food, aggressive chemicals, radiation, and other things that can lead to the mutations which can be attributed to radiation. You know, Greg asks a great question, why use the word radiation? Maybe a less ordinary word like emission. Well, this was tried for a bit. It used to be, we didn't even call it nuclear, we called it atomic energy. And then that was linked with atomic weapons. But now the whole idea of, you know, in the fusion world, we're calling it fusion power. People don't call it nuclear fusion because they want to get away from that kind of stigma. I believe in using the words that I mean, despite the fact that they may cause fear, because I'm also up for some education. So I would like to teach people not to fear the word radiation, knowing full well they may come into the argument with a fear of the word radiation and of radiation itself. So let's see. So Sivesh asked to just clarify something. What are we counting in counts per second back in our detector? I'll go back to one of our spectra. So we're counting the number of confirmed gamma rays that have entered our detector. It doesn't necessarily mean that our detector caught every gamma ray that went through it, because many of them go flying through the detector. In fact, very few of them actually, with this efficiency of less than 1%, most of the gammas that hit our detector go right through. So we're counting little pulses of charge that our charged particle detector picks up. And we're dividing by the number that we know ought to be going through from a calibration source to get this into radiation counts. And so Chris, great. I love these questions. Is radiation a vector or a scalar? The way I'm presenting it, it's a scalar quantity because it doesn't have a direction. However, you can express radiation as a vector quantity if you call it a directional flux or a current. Like if you're building a particle accelerator and you want to know the number of protons being fired down your beamline, you better believe that has a direction, and that current has a vector. So the way I'm presenting it, it's a scalar, but you can also define it as a vector if you want to know its direction. Mel asks, should parts of Chernobyl exclusion zone be reopened safely? I believe some of them can, but only after very careful measurement and not just walking around with a Geiger counter, but making sure that there aren't any plants, animals, other things that are concentrating and accumulating dangerous amounts of radiation. Two of the things that are most known to do this are moss and mushrooms. And people pick mushrooms around Chernobyl and Ukraine all the time. I would not go picking mushrooms in parts of this Chernobyl exclusion zone. And Inga, I'm delighted you asked this because this is going to be my launching point. Can I talk about radiation levels following nuclear accidents? Yes, I'm going to cover that next when we talk about Fukushima. So let's talk about the Fukushima accident. The Fukushima disaster, and yes, it was a disaster, was comparable to Chernobyl. This is what I've heard. Filling the oceans with dangerous levels of radioactivity, and eating ocean seafood has become more dangerous. I've heard this myth countless times. I've been to Japan after Fukushima. Some people are still afraid to eat produce from Fukushima. After the accident, places started saying the country of origin of seafood just to prove that it wasn't from Japan. And while some of this caution was warranted, it is a lot of ongoing economic damage without a lot of reason. For example, they still, in the Fukushima fish markets, you can even see this on YouTube videos, they test every single fish to check for radiation. And the quote at the end was great. They said, "We haven't found any yet, but we're never going to stop looking." So the economic damage to the Fukushima region has been horrendous. Let's get into that. People may have seen this image before. This was an image that had graced lots of news articles and magazine covers and all sorts of things, labeled a radioactive nightmare. This image has been strategically cropped, either intentionally or not, by whoever made this magazine cover and many, many other sources. And this is where I'm going to start to get mad, because whether it's intentional or not, it's either criminally negligent or willfully ignorant. This is the full picture from where it came. This is an image from the National Oceanic and Atmospheric Administration. You notice anything suspicious about this? Well, let's zoom in on that scale bar. The units of this purported graph of radiation are in centimeters. Radiation is not measured in centimeters. It's measured in becquerels, disintegrations per second, or curies, or radiation dose is measured in energy absorbed. This is a map of the height of the Fukushima tsunami immediately afterwards, which has been misattributed visually to radiation. So myth number one, this is not a map of Fukushima radiation. This is, however, in terms of monitoring station measurements of becquerels per cubic meter, disintegrations per volume of 137 cesium found in the ocean. So the way you know this is good, it's in the right units. It's from a peer-reviewed source with a link in a digital object identifier. And it quantifies things, like the paper's got uncertainty in it. It's everything you want. So let's now start tackling this problem and ask, did Fukushima release a dangerous amount of radiation into the oceans for today? Later, we'll talk about the days immediately following the accident when the answer was yes, it absolutely was dangerous levels. Let's talk about now. So there's been enough time since the Fukushima disaster that there have been many studies and review papers quantifying how much radiation in terms of becquerels. The P stands for peta, or 10 to the 15th. So there have been petabecquerels of atmospheric fallout. There have been terabecquerels and petabecquerels of discharge into the ocean. And so we're talking here on the order of 10 to the 16th becquerels of radiation. On its own, that is a disgustingly large amount of radiation to consider it in one place. But now I'm going to ask you to consider the size of the ocean. So let's compute the specific activity of the ocean before Fukushima and how much it went up because of it. If you want to say this problem worked out with no steps skipped, you can go to the 2201 Lightboard lectures, which are available online. But going with the IAEA source, the ocean started out with 11 becquerels per liter of seawater. Each liter of seawater gives off 11 disintegrations of radiation per second, mostly from the same potassium-40 that we find in our bodies. And looking this up, also from the National Ocean and Atmospheric Administration, there's about 10 to the 9th cubic kilometers of water in the ocean. That's about 10 to the 21 liters. According to a review of about 25 different model studies, Fukushima released about 27 petabecquerels of radiation, mostly in the form of cesium existing in the ocean now. And when we divide 27 petabecquerels by 1.3 times 10 to the 21 liters of ocean, we get an additional 0.00002 becquerels per liter on top of 11. If that isn't the mathematical definition of a drop in the ocean, then I don't know what is. Now, that does not mean that levels were never significantly elevated. In the days following Fukushima and the weeks and months, the additional cesium in coastal waters outside Japan exceeded the normal levels. Let's say it doubled or tripled or near the plant even more. So there was a gigantic increase near Japan immediately after the accident. What we do know, though, and I'll get to this when we talk about waste, is that nuclear isotopes undergo exponential decay. There's an increasingly, about half of it decays every what's called half-life. And the cesium-137 half-life is about 30 years. So after 30 years, half the cesium released will be gone. And also the ocean is gigantic, and it takes time for that radiation to dilute in the ocean. There's a solution, an expression I learned from my Navy colleagues in grad school. Dilution is the solution. And as sort of like anti-environmentalist, that kind of sounds to me, they sometimes have a point. So the Fukushima disaster was not quantitatively comparable to Chernobyl. It did release huge amounts of radiation, but not as much as Chernobyl. And because it released it into the ocean, that actually mitigated the effect somewhat. Now, it's true that the radiation doesn't immediately distribute uniformly, and it does bioaccumulate in things that tend to absorb cesium. But like I mentioned, from the people that are measuring radiation in fish in the Fukushima fish markets, they're not detecting elevated levels. There are probably some cesium in there, right? I would be willing to bet money that in the most sensitive detectors, you can detect excess cesium. But in terms of detecting a unsafe amount, hasn't happened yet. But it is a literal drop in the ocean. So Inga, I hope that addresses your question directly. And I'd love to break for some more questions about fission reactors, nuclear accidents, Chernobyl, Fukushima, 3 Mile Island, anything you'd like. So Larry, do you want to start me off with any pre-submitted questions, or should I jump into the Q&A?
I think jump into the Q&A. They're coming in quite a bit already.
Sure. Okay, so Michael Golan has one about the fear of decommissioning the Pilgrim reactor in Plymouth. What about waste disposal into Cape Cod Bay? So that shouldn't happen. However, there is a lot of radioactive water involved in both cooling reactors and in the Fukushima case, in keeping the core cool. So in terms of, I'm not aware of a plan to release anything to the Cape Cod Bay, but I'm sure that there is a little bit of tritium getting out, and it may be detectable, but it is not allowed, and it will not happen that a dangerous level can be released. The spent fuel, which I'm going to get into next, I'm glad you asked this, Michael, because my next thing is about nuclear waste and what it looks like, is contained in steel-lined, concrete-reinforced spent fuel canisters. I invite all of you to look up stress testing nuclear canisters on YouTube. They do the most fantastic experiments. They'll strap these things to a rocket-powered train and run it down a track at about 120 miles an hour, and have another rocket-powered train with a giant spike on the end coming onto tracks in the other direction, and let them crash into each other, and then douse the whole thing in jet fuel and light it on fire. And the casks don't break. And they drop them from 10 feet in the air onto a metal spike, and they don't break. And they put explosives around it, and they don't break. Nuclear waste canisters, they haven't leaked here yet. There are other lower level forms of waste that are not as rigorously kept that have leaked. And there is legacy waste from the early days of the nuclear programs, like at the Hanford site, that have been leaking. And so it's not that we've never had nuclear waste leaks, but the way we do reactor waste nowadays, it's not happening. What happened in Fukushima is there are millions of gallons of tritiated water that have been used to cool the reactor, and they are thinking about discharging that into the ocean. But again, the goal is to dilute it to safe levels before you further dilute it in the ocean. They're basically saying, well, there's a risk to storing it on site. What if it leaks and gets into the groundwater? Then you'd have a pretty direct route to people's livelihoods, or we can dilute it. And so in this case, this is absolutely a lesser of two evils. Nobody wants to release radioactive waste anywhere. I hope. I really, really hope. But in this case, the goal is to do, if you can't do no harm, do as little harm as possible. And then, Mr. or Mrs. Zoom user says, what would I say in Germany? To Germany in response to their decision to shut down nuclear power? I have a couple slides on that specifically for Germany. Monty asks why only discuss cesium. Their longest lasting isotope that is released in significant quantities. For example, shortly after nuclear accidents, a lot of radioactive iodine is released. But this has a half-life of 8 days. So in about a month or two, the iodine's all decayed away. And this is why, after a nuclear accident, people are issued iodine pills. You fill your thyroid with non-radioactive iodine so that your thyroid, which absorbs iodine, doesn't absorb the radioactive iodine. And after a couple months, you don't have to take them anymore. because the iodine's all decayed away. So Joe asked, is U.S. naval reactors the operator of the most fission reactors in today? In the U.S., absolutely. There's about 100 reactors on land and more than 3 times that many in the ocean. They're called submarines and aircraft carriers. So when people just say, oh, there's no nuclear reactors in this or that country, I'll say, well, you should check offshore to see if there's a nuclear sub in your waters. And those are also operated with a pretty fantastic safety record. And let's see. Oh, interesting, Joe. I've heard that France actually imports nuclear waste from other countries, which they reprocess to use as fuel. Is this true? I don't know that, but knowing that France reprocesses it would not surprise me, because getting rid of nuclear waste is a hard thing to do. And if you can get it out of your country, your constituents will probably be pretty happy about that. And if France is already reprocessing waste and they say, well, let's add to the pile, I wouldn't be surprised if that's the case. So let's see. So Stan asks, what are the most attractive reactor types for commercial use? That definitely depends on who you ask. I'm not ready to answer that question, though I will say right now, there are a slew of advanced reactors that use coolants that aren't water. Things like X Energy's helium reactor, TerraPower's natrium reactor, Kairos's molten salt reactor. Without using a coolant that can easily boil away, you eliminate the possibility to have accidents like Chernobyl or Fukushima happen. There are other accident scenarios that can happen, and we don't know the likelihood of them happening because they haven't happened yet. We don't think they're very likely. Now, at the same time, I'll tell you a quick story I heard about predicting low risk or low probability risk. This was told to me third or fourth hand, so I wouldn't verify it, but it makes for a good story. When the 787, the Boeing 787 was being touted, they said 10 to the minus 9th approximate mistakes per flight hour, which means you'd have to have 1 billion flight hours in the air for something to go wrong. And there was some grumpy engineer somewhere that just said, I don't believe it. I don't believe numbers that little. And so during one of the test flights, the plane encountered what's called a tail strike, where the tail got a little bit too close to the ground on takeoff, and it scraped a little bit. And that same grumpy engineer said, oh, so that's what 10 to the minus 9 looks like, in a very sarcastic tone. Again, I can't confirm this story, but it does make for a neat anecdote about trying to predict really rare events and how right or wrong you could be. So let's see. I think Monty wildly discussed cesium. I think I may have already answered that, since cesium is the long-lived one that gets everywhere. So shorter-lived ones like iodine are quite short-lived. Super long-lived isotopes, for the same amount of material, the longer the half-life, the less radioactive it is, even though it stays radioactive for longer. Let's see. Okay, so Larry says, you mentioned that people from Fukushima could have, the Fukushima thing could have been avoided. They had secondary coolant tanks a little higher to allow gravity-fed emergency passive cooling. Were you right? While I don't know the specifics of the Fukushima plant, you are right in that passive cooling is the strategy to mitigate beyond design basis accidents, like things you never expect to happen. Now, I have a great story to share with you. There is a reactor that was closer to the epicenter of the earthquake called Onagawa. It's the, what was it? When I first went to Japan as a MISTY intern, on day 2, they took us to the Onagawa plant, and we were analyzing some small cracks that they had found in the piping. I got the opportunity to go back there in February of 2020. If you think about how close that was to the temporary end of the world, that's like the last thing I did before the pandemic hit. Got to crawl around underneath the reactor and see why it survived. Despite being closer, despite being hit with a higher tsunami, they put their diesel generators and their passive cooling tanks and all sorts of other stuff and backup systems at higher ground. And they had a higher seawall, and they survived. And they're restarting soon. So the reactor that was closer to the earthquake and tsunami than Fukushima is about to restart. So Larry, in terms of doing a little bit of planning, really goes a long way. When you consider that these things are $10 billion assets, what's another couple of meters of seawall in terms of creeping conservatism? That doesn't sound creeping to me, right? So Larry, I'd wager that you're right. So let's see. I think that's good for questions because I've been at it for a bit. And I do want to address the waste. So we'll get there in just a sec. Let's get the Germany question next, and then we'll hit the waste. So I've heard two myths, and these are going to be short ones because I'm just going to show you the data. Nuclear power plants still emit too much CO2 to be part of the climate change solution, or nuclear power is too dangerous to be part of the solution to climate change. These are both false, and I'm going to show you why. Let's quantify these with peer-reviewed sources. These unquantified myths don't mean anything. Let's look at the numbers. Depending on which study you look at, you may find that nuclear power all in, including the concrete and the metal, including the disposal costs, including the cost of making the materials, sometimes nuclear edges out wind and solar in terms of its total carbon footprint per megawatt hour. This part is important. We're normalizing for the amount of power this thing makes. So for example, a 1 megawatt solar plant is always going to have less carbon intensity than a gigawatt nuclear plant. But you've got to compare a gigawatt of solar to a gigawatt of nuclear. Depending on the other studies you see, nuclear power might get edged out by tidal power or geothermal or offshore versus onshore wind. So first of all, this shows you there's no such thing as follow the science. If we learned anything from this pandemic, it's when someone says follow the science, you should stop them right there and say, what do you mean? What are your sources, plural? Not just what is the one paper that agrees with your predetermined conclusion. Regardless of which side of what issue they're arguing, you got to exhaustively look at all sources, which you can find both in support and in opposition of your hypothesis. However, that's not the question we should be asking ourselves. One study shows nuclear is the lowest carbon. One study shows nuclear is not the lowest carbon. I don't care. All of these technologies, which are super, super, super low carbon compared to gas and coal and oil, you're looking at the climate change solution. All of them together with their strengths, weaknesses, and the security that comes from energy diversity. So if anyone ever starts arguing nuclear shouldn't be part of the solution because the concrete emits CO2, just tell them to shut up. Why are you even saying that question? We should be focusing on stopping climate change, not arguing over which source of energy is a little bit better than the other one. Because while we're splitting hairs over CO2, the effects of climate change are manifesting themselves in terms of relocations, droughts, famines, deaths. It's going to come to deaths. Same thing. So nuclear and renewables together are our only ticket out of this climate change challenge. I don't know a nuke alive that wouldn't argue that renewables are a big part of the solution for climate change, because you need baseload power and you need peaking power. And luckily, we're all awake when the sun is shining, for the most part. I happen to do my early running runs at like 3:30 or 4 a.m., but I don't consider myself part of the norm. So for those of you on night shifts or those who used to do that, we're somewhat in the minority. But luckily, we have a lot of solar power and wind when we need it, but we need a base load of something like nuclear or hydro as well. Now let's get to the dangers. And some of you may have seen this STAR forum where the topic of nuclear safety and deaths came up. This is one of the sources of data that is so often exaggerated and it's so unimportant. So let's show here, we're showing number of deaths based on all deaths and accidents and air pollution per terawatt hour of electricity. We're normalizing the deaths per amount of electricity produced. And what comes out on top again? Coal, oil, and gas. Because here the cost of CO2 wasn't counted for, but so is the cost of pollution, the carbon intensity of coal mining, the deaths from coal mining, the occasional explosions that happened, like about 20 years ago. One of the coal plants at Salem, the town next to where I grew up, just blew up, killed a few people. And look at the bottom. It's the same three. Wind, solar, and nuclear are all pretty damn near zero. I would never bring up the idea that according to the study, nuclear is safer than wind. That is not the point. Nuclear, wind, and solar are all extremely safe, and they're comparable when accounting for everything, including the deaths from radiation and accidents. That includes the 4,000 to 11,000 deaths attributable to late-stage cancers from Chernobyl. You may see numbers like up to 6 million. You need to question those sources. I've seen people even say that tens of millions of people are going to die from the fallout from Chernobyl. This is a question of, well, first of all, where does your numbers come from? Do they come from peer-reviewed sources or anecdotes? And just because it's peer-reviewed doesn't mean it's correct, right? Just because it's published doesn't mean it's right. What other confounding variables could explain some of those other deaths? And so statistically speaking, let's take the 11,000 upper estimate. Nuclear is pretty safe, right down there with wind and solar. Within margins of uncertainty, all equally good, in my opinion, because we need everything we can get. As a nuke, I would never advocate for 100% nuclear power or anything even close, probably not even 50%. The more diversity, the fewer common mode failures you can have. And so some lessons to remember, no matter what side of the fence you sit on, including if you're sitting on the fence, whether you're for or against nuclear power, I hope I've taught you to check multiple peer-reviewed sources and to question your assumptions, including your own. To express quantities comparing the same units. The source of so many of these myths is comparing two numbers in different units, or sometimes in the wrong unit, as we found. To normalize for specific activity, for deaths per terawatt hour, to make sure that you're arguing about the same question. And don't forget the big picture. Be a systems thinker. If you're splitting hairs about whether wind, solar, or nuclear is safer, ask yourself, well, what is the lost opportunity cost by not having them and keeping more coal plants on the grid right now? So that's kind of the message I give you is I'm not here to argue pro-nuclear. I'm here to argue pro-data, pro-science, which does not mean follow the science. Don't follow anything. Go and make your own informed opinions with a little bit of math. You can start to answer a lot of these questions for yourself. So let's take a break for some of the questions about climate change and renewables and nuclear power together, because this is one of the hottest button issues. I'd love to hear what you think. So Stan asks, are there significant limits on nuclear fuel availability to meet global energy needs? That is a good question. In terms of known uranium sources available for the immediate, like light water reactors, we've got a few hundred years. In terms of breedable uranium, in terms of making fast reactors that generate some of their own fuel, there are thousands. And when it comes to fusion, because there's plenty of deuterium in the ocean, and fusion plants produce tritium, which is the other component of their fuel, it's an inexhaustible supply. Getting started is a little bit of the tricky part, but we know how to make tritium now in fission reactors. And Monty asks a great question. Why do we need to do a new design every time there's a new reactor? Why don't we have copy exactly? There was a couple more questions further in the chat about small modular reactors, and those questions are the answer to Monty's question. So small modular reactors are taking exactly this philosophy to say, instead of making a gigantic new plant that, by the way, utility companies don't want to buy anymore, and making it different every time and making all the new mistakes all over again, why not just make lots of little reactors? That's what the new nuclear companies are doing. I'm proud to say that there's a phrase now called nuclear startup. And I heard early on the chat, some people have invested in them. It's awesome. Now, their goals here are not to make gigantic gigawatt plants, but if you talk with folks like X Energy, we're talking little 100-megawatt plants and making dozens of them at a time. So by the time you've made a couple dozen, you've worked out the kinks, you know what can go wrong, you've optimized processes, and you get the capital cost down. This right here gets at one of the questions. Why is nuclear so damn expensive? Because every reactor in this company that's on land, every reactor in this country that's on land has been the first of its kind. And we make all the same mistakes and all the same budget overruns and all the same delays. And if we didn't have to do that anymore, that's what would really cut the capital cost by factors of 2 or 3 and make nuclear not prohibitively expensive. So interesting, Sandy asks, are there any new techniques on the horizon for countering diversion in spent nuclear fuel processing or the use of fuel for weapons production uses? I will say it is hard but not impossible to illicitly reprocess spent nuclear fuel and extract the plutonium or high enriched uranium. It is easier, that's a relative term, to enrich new uranium. This is something my group actively works on. We look at radiation damage to fantastically low levels to the materials involved in making high enriched uranium in enrichment centrifuges. And so we're looking at repeatable sampling techniques that a group like the IAEA, the International Atomic Energy Agency, could send its teams of inspectors into let's say, one of those countries that might be making nuclear weapons that I'm not supposed to talk about, and go in and tell for certain, has this facility been used to make weapons? And if so, how many? And so, Sandy, if you want to get in touch later, I'd be happy to show you the details of the research we're doing and some early promises for what might be happening. So let's see. Oh, yeah. So Ken asks, people worry that radiation will last for thousands of years, like Yucca Mountain, but presumably that energy is spread out in time, potentially to unharmful levels. What is the right way to think about this? I'm glad you asked, Ken. So let's get into waste, because this is going to answer your questions. There's a myth that all nuclear waste has to be stored effectively forever, will have to remain highly dangerous for millions of years. And the truth is some of it, not all of it. And so we need to look at the difference between levels of radioactive waste, how much, and when they decay. So to get a little bit back into the math, all isotopes decay via exponential decay. It's one of the truly random processes in nature that follows Poisson statistics. The likelihood that one atom decays after a certain time after a previous atom decayed does follow Poisson statistics. It's pretty cool. And the net effect of this is that you have what's called a half-life, where every amount of time, the half-life, you lose half of the radioactive isotope, and the radioactivity decays by a factor of 2. Now, this is the curve for a pure amount of one isotope. If you were to add a bunch of isotopes together and you start looking at their combined radioactivity, the picture starts to look a little different. So shown here on a logarithmic scale is the radioactivity of 1 gram of each of the 9 isotopes of scandium. This is a problem I give in 2201, where I say calculate the amount of time it would take for 9 grams of scandium, all equally distributed among isotopes, to decay to a safe level. And it may look like it suddenly drops off the face of a cliff. That's because this time axis is in log terms. This is a logarithmic timescale. And so what you can see here is that each of the isotopes has its own decay curve, which on a log-log plot, this is what an exponential function looks like. It just decays down further and further and further. And by the way, yes, it does cross the x-axis. It does go below 0, because this is a log axis too. The log of a very, very small number is a negative number, and that's how it's plotted on this graph. And so what you have to ask yourself is, if I sum up all the amounts of all the isotopes in nuclear waste, when does it reach some threshold value where it's the same as the dirt it came from? And at that point, you don't have to worry about it. But this is a pretty hotly debated question. So for example, there are many amounts of and classifications of nuclear waste. You can see that with a longer half-life or a higher radioactivity, let's say things that are very short-lived and they're very not radioactive, we'll call it very short-lived waste, which means you just store it on site for a little while, days or weeks. In my lab, it can be as short as hours, and then it's effectively below background. It never ceases to be radioactive, but almost nothing ever does. And as long as it's at background, it's effectively, legally not radioactive anymore. Things below a certain level is called exempt waste. Like, yes, it's radioactive waste, but the levels are so low that they don't pose a danger to anyone, and they can just be thrown in the landfill. Even the next level up, very low level waste, can go to the landfill. In this case, dilution is the solution. For low level waste, that's not that dangerous. You may not want to put it in a landfill because you don't want it to get into the biosphere, but you can put it in near surface disposal. And then the more dangerous the stuff is, the further away you want to keep stuff. And fission reactor fuel is in this highest level category. I should mention, though, that a reactor only makes enough of this high level waste to fill about 3 refrigerators per year. Now, those would be some disgustingly radioactive refrigerators, and you would want to, let's say, drill boreholes kilometers into the ground to store them, because we don't have something like Yucca Mountain where we can hollow out a mountain and put them in. But that actually is a political reason. They actually built it and they weren't allowed to open it. So right now we have places like the Waste Isolation Pilot Plant, or WIPP, where these canisters of nuclear waste are brought down by truck or elevator and put into this deep geological repository at about, let's see, what does that say? 2,150 feet below. The ground is a great shield of any radiation. And at the same time, you can tell these things are not very radioactive because there's a dude standing next to them. and people actually go and deal with that stuff. This here is a picture of spent fuel nuclear waste sitting outside a nuclear reactor. Because Yucca Mountain has not been allowed to open, nuclear plants are keeping their waste just outdoors on site in these incredibly safe canisters that we smash on trains and set on fire with jet fuel to test them. This is not the long-term storage option we want. We do need a place to put them where it's going to be further away. And we are looking for places that have been bedrock stable for hundreds of millions of years, like primordial oceans that are now just salt rock in the earth. And if they haven't moved in the last 200 million years, the chances that they'll move in the next 10,000 before we, I don't know, leave Earth in search of a new galaxy or something are very low. But that still begs the question, the waste is going to be there. And there's always a chance that someone's going to dig it up. So what do we do about the waste that'll last for millennia? How can we ethically justify its existence? And how do we warn future generations of its insane toxicity? Well, for the ethics, I would counter and say climate change is real, it's here, and it's now. And I would treat nuclear waste the same way I treat fossil fuels. I don't hate them. They got us to the standard of living where we are today. So I would say use what we absolutely must, thank them for their service, and transition off of them as soon as possible. So as someone who grew up in the fission world, I see fission as a bridge to a grid purely made of renewables and fusion power. I don't want to see us using fission power for the next 1,000 years. One, that's going to mean that fusion didn't work and renewables didn't pan out. Two, we don't want to make nuclear waste. We especially don't want to make high-level nuclear waste or anything that could be diverted to make a weapon. So to us, this is the highest tech thing we have for the interim time. And with anything that has benefits, it has drawbacks. When you move energy from one place to another, you lose some in terms of entropy. When you make something new, you generate waste. And it's our responsibility to make sure that that waste is dealt with safely, ethically, including thinking tens of thousands of years into the future when humans might not look the way we do now. We may not share any languages. We may not have any symbols. There could be an electromagnetic pulse that wipes out all digital data. How do we warn future generations of this toxicity in the event of no record of the past, not harming generations 10,000 years from now? Well, there's a documentary that tried to tackle this called Containment, which I highly recommend folks watch. It's the most politically neutral, don't take sides question, saying, what do we build to tell sentient, intelligent beings that may not speak any of our languages or have any of our data, don't dig here, it's bad news. This was actually based off of some national lab studies where they convened engineers, scientists, nukes, philosophers, anthropologists, social scientists to ask linguists to answer this question together. And so this is actually an active area of debate. And this movie was spurred on by these national lab studies to say, what could go wrong 10,000 years from now? And how do we design these places to have geological lasting significance to future civilizations that we have no idea how they're going to work? So I thought that was kind of fascinating. We are thinking about these things, and it would be unethical not to, because even if fission bridges us to fusion, and then we end up with a carbon-free, fairly waste-free energy stream, the nuclear waste is still going to be there. A question I often get, and I don't know if it's been asked in the chat. Thank you, Stan, you just asked it. Why not send the high-level wastes into space? In 500 years, when launch feasibility will be perfect. You answered my question. So right now, I don't know if anybody saw the recent SpaceX launch, but it didn't quite make it. If there's any chance that nuclear waste could be on one of those rockets that we're blasting into space and it comes raining back down on Earth, that's not acceptable. But like Stan said, let's say we get to a point where launching becomes 100% reliable activity. Then you might think about getting waste off this planet and solving this problem once and for all. Never mind that it's going to go somewhere in space, and I don't know what would happen if you shot nuclear waste in the sun. I sure hope nothing would happen. I can't imagine what would, but that's a question for an astronomer and a star physicist, not me. And so now I just want to open it up to anything. We've touched on waste. We've touched on renewables and nuclear. To get back to the Germany question, they're celebrating that they shut down their last nuclear plants. I'm watching their CO2 emissions go up. My wife's from France too, and she just said, oh, growing up, we love our cheap electricity. And we love, love, love how much Germany has to buy to meet their carbon goals. So I feel sorry for what the German public has been sold in terms of a narrative. It's very country specific. It's interesting what different countries and cultures decide to do with the same information. But to meet one's climate goals and exclude nuclear from the solution is to be tying a couple hands behind your back. So I'm not mad at Germany. I'm sorry for them. So hopefully that answers the Germany question. How likely is it that fusion will be economically feasible? No one's ready to really answer that question. The fusion companies will tell you, we're ready. The fusion detractors will say it'll only be here in 50 years, just like we said 50 years ago. The real answer is an unknown point in the middle. There are a lot of technical challenges that have to be solved before fusion power is going to be technically feasible, and then additional ones have to be solved before it's going to be economical. What I would say, though, is if we don't start working on it full force, we're just delaying the end result. And the end result might end up being catastrophic failure. But to give you a little bit of confidence, at least from my semi-professional opinion, I shifted most of my research group from fission to fusion materials because I think it's going to work if we work hard enough at it. So hopefully, Somanathan, does that answer your question? I hope. Let's see. Zumu's user asked, don't those waste canisters generate heat? Do they have to be separated by a certain distance? Absolutely. They do give off what's called decay heat, because everything that undergoes radioactive decay, a lot of that radiation is reabsorbed and comes out as heat. And so if we look back at the canisters, I'm going to zoom into a little part of them. So I want you to notice right here, there are some vent holes on the bottom and there's some vent holes on the top. And that's because the canister inside is making heat, and this naturally pulls in cooler air and ejects it out the top and sets up natural convection currents. This is a form of passive cooling. And one of the things that waste canister folks worry about is what could clog those channels. Could corrosion deposits or other detritus clog those channels? So keeping those clean is one of the things that you have to do in terms of nuclear waste. So very good question. Let's see, Larry, maybe now, do you want to open it up to some of the pre-submitted questions, since that's all the slides I had, and I want to save as much time as possible for some debate.
Yeah, you're incredible. You, as a source of facts and the ability to articulate them, is just phenomenal.
Thank you. Yeah, I'll tell you what, I'll stop sharing so you guys can see me too.
All right. Do you want to talk about fusion in a little more detail, perhaps? You know, where you think we are in terms of the technology development?
Sure thing. Yeah, as the associate director of the PSFC, I've got a nice kind of bird's eye view of this. And as a relative newcomer to fusion, since I'm not a plasma physicist, I've been coming at it from a fission and systems expertise. One interesting thing is, in terms of fusion or smashing nuclei together, is pretty different than fission or blasting them apart. But once you get far enough away from the fusion core or the fission core, the plants start to look the same. They've got power cycles of similar sizes. They'll have siting requirements. They will generate radioactive waste, although the waste from fusion is going to be so many orders of magnitude less active and less in volume. And there are some specialties to them. There are plasma-facing materials in a plasma. There are nuclear fuel rods in a fission reactor. But a lot of the stuff, even the coolants, temperatures, and pressures, are shared between many fission and fusion designs. Now, there are three main technical risks left, in addition to all the little ones, before fusion power is going to be a technical commercial reality. One of them is the magnets that are strong enough to squeeze the plasma so that it's dense enough to fuse and doesn't hit any of the sidewalls. And that was largely solved 2 years ago by a team at the PSFC, led by my colleague, Zach Hartwig. 20 Tesla, something that you could walk through. And so that's the biggest magnet in terms of size and field strength combined by a lot. And the cool thing is, this was double the field strength of the last magnet design. And you heard Dennis White speak before, fusion confinement pressure goes up with magnetic field strength to the 4th power, doubling the field. let's use 16 times as much confinement power, and that lets you make your fusion reactor smaller. Small to the point where you can build the components in things we have today. Unlike whatever is going to happen for the ITER or demo reactors, ITER is probably going to be built. And this is a physics device. The demo one, that's like 6 times bigger than that on all sides, I don't know how it's going to be built. But something as small as many of the other fusion companies' designs that are making it faster and smaller, this is, here and now buildable. The second big risk is tritium breeding. Fusion reactors have to make more of its own fuel than they consume. That hasn't been demonstrated at scale yet. We're working on that at MIT in an experiment called Libra, which is supposed to be the world's first ton-scale tritium breeding experiment. And I mean ton literally. We bought 1,000 kilos of the molten salt that we're going to be using to breed tritium and to test how well it works.
What's the name of the project? What's the name of it?
It's called Libra, Libra.
Yeah.
It's a US government funded project. So thank you, US government, that's for taking a risk on this. This is really cool. The third challenge, and this is where my group comes in, is materials. At the end of the day, things tend to be made out of materials. And we haven't decided what those are going to be for fusion power yet, but we're getting close. We're leveraging 30 to 50 odd years of experience designing materials for fast fission reactors and eventual fusion reactors. It's been a lot of smart people working on this since the 50s. And we're at the point now where we want to down select the best of those compositions, optimize them, and start getting neutron irradiation data so we can be sure that when we build a fusion plant, I have no doubt that the first fusion plant will turn on and make fusion power. What I don't know yet is it going to last for 40, 30, even 10 years and be economical? That's what materials reliability is going to tell us.
Yeah, the economics and the reliability, but those are so important in the energy space. All the energy companies have to compete on price. And are you going to be in business in 30 or 40 years? And who's going to fix my gear?
Exactly, because these are, even the small fusion plants are billion-dollar assets. Yeah. You don't start making money from them by selling electrons for a while. It's going to be order years for the small plants, order decades for the big plants. That's how fission reactors work now. You don't start making money back for on the order of 20 years or so for a grid scale fission plant.
Yeah. So SMRs, what you talked a little bit about that, maybe go into a little bit more depth on that, where you think, are we going to have hundreds of SMRs scattered around the country? Do we have to worry about terrorism with regard to those?
Sure.
How can they be hardened?
Yeah, so SMR stand for small modular reactors. The goal is that they're at least an order of magnitude smaller than the ones that we see now. So right now, the big reactors are gigawatt scale. Small modular reactors are kind of hundreds of megawatt scale and smaller, as small as could fit on the back of a truck at the sort of 1 megawatt scale.
Right.
So while the amount of materials versus the amount of megawatts, that ratio is a little bit higher, the cost for, some people are asking these questions about nth of a kind reactors. Once you make 20, 30, 100 of them, you get good at it. And it costs a lot less to make each one, even though each takes proportionally a little bit more materials to make. Now, in terms of terrorist threats, in terms of accidents, there's also a serious safety benefit in getting less power dense. So in terms of the amount of damage that the same attack could do in a smaller plant, when there's more materials keeping less radioactive stuff in, it scales better. I'll give you an example. Nuclear plants right now are required to have a lot of system redundancy, and some of the backup systems not only have to have multiple, but they have to be on different sides of the containment building, such that if somebody were to fly a fully fueled plane into the side of one, it would shield some of the other backup systems. The dome itself would shield it from the wreckage. And so we're never going to get away from the need for safety and redundancy, planning for design basis and beyond design basis accidents. But when you think about it, if the reactors get smaller, the decay heat goes down. So after a few hours, a reactor will still produce about 1% of its original heat just from radioactive decay. For the case of a gigawatt thermal plant, that's 10 megawatts. That's a lot of power. That's almost double the power of the MIT nuclear reactor. And we have the second toastiest research reactor in the country. If you have
only the second?
Only the second to Missouri Tech. They've got 10 megawatts and they've got SB. If you have a 10 megawatt reactor and you cut that in down to 1%, now you're talking about 100 kilowatts of cooling. That's not that hard. Considering that automobiles operate in the sort of many tens of kilowatts, you're now talking about cooling the heat generated by a couple cars instead of a couple MIT reactors. So being able to get cooling water and emergency equipment around a smaller reactor is proportionally easier.
Yeah, fabulous. So, when Jacopo gave his talk back in the fall, he mentioned nuclear batteries. Maybe you have some comments on nuclear batteries?
Sure. So by nuclear batteries, he's talking about very, very, very small reactors and ones that are fueled for the lifetime of the reactor. So they don't need to be opened up and refueled. It's really just something that you drive to a site, you plug it in, it makes electricity, and at the end of its fuel cycle, you return it. This is a fairly old concept. There was something called the, I forget this is the PRISM or the SSSS reactor, but the goal was you want to sell nuclear power to countries that you don't want making nuclear fuel. You could sell them these tamper-proof reactors that it's very obvious to tell if something's happened. And when the reactor has spent all its fuel, you ship it back and you get a new one. Now combine that with this whole small modular reactor idea of making dozens or hundreds of tiny ones, and you've all of a sudden got a plug-inable little nuclear reactor. And where you think this might be useful is maybe this isn't useful at the gigawatt grid scale. You wouldn't want to power a city with nuclear batteries because of the amount of stuff involved. But now you start thinking about remote mining communities, villages on the coastline of Alaska, where the anecdote is it takes 10 gallons of diesel to deliver a gallon of diesel, where the energy intensity is 10 times higher. The energy prices can be more than 10 times higher. There are some great markets for nuclear batteries. For offshore, you could think about nuclearizing more of the shipping industry, because I don't remember the exact numbers, but it's something like the 6 biggest ships produce some ungodly fraction of ocean-borne pollution. So it's not just about electricity, it's about transportation. And when you've got nuclear batteries that could produce thrust and onboard electricity, you can start talking about decarbonizing shipping.
Absolutely wonderful. Mike, you were just fabulous. Here's a question. There's been a sea change in the last 18, 20 months here in the United States with the change in administration and the IRA and all the federal money that's coming out. And then plus in the venture community. The venture community is funding huge amounts of nuclear projects now, which they weren't 2 years ago, which we were not doing that. So with this change and the increased excitement about nuclear, what are you most worried about? Say 10 years from now, if you look back, what might we have missed?
Sure, that's a great question. There's, I'd say, 3 things that come to mind off the top of my head. The most realistic scenario that I worry about is that we don't get over ourselves and we hem and haw about the risks of nuclear and we let climate change get 10 years closer. Because that's the most likely thing to have happened, is that we are too worried about causing some damage, and then by our inaction bias, right? Our bias that we don't perceive ill effects from doing nothing as much as we do doing something, we allow climate change to start causing far worse effects. I ran through Arlington, just the town next to Cambridge, a couple weeks ago, and they put up a plaque at about 3 feet high on one of the stop signs that says 2039, Arlington permanently under 1 foot of water. And that's what some of the projections say. By 2050, MIT is going to be under 3 feet. I do not know the veracity of those claims, but they're scary. And we are already seeing floods in places that we never used to see them. So my real fear, it's not of a nuclear accident, it's not of something, it's that our inaction bias paralyzes us as a society.
I've just got a couple of more questions here. It's 7 o'clock now. 7 o'clock here.
Sure.
10 o'clock.
I can go all night, so I'm happy to stay on.
I know that, yeah. So I think I know the answer to this, but I thought I would throw it out anyway. do you see, this is from Paul, do you see fusion power opening up a migrating path for processing radioactive waste from fission power?
Well, that's an interesting question.
You know,
Now, it is true that
it,
if you put radioactive waste in a neutron field, you do transmute it because it'll absorb neutrons, and some of those long-lived isotopes could become short-lived isotopes. There's a balancing act, though, because you want those neutrons to produce tritium to produce fuel for fusion reactors.
right.
So for the first dozens of reactors where the name of the game is going to be make more fusion fuel, I don't see that as an economic prospect, because then you're robbing Peter to pay Paul. But once things get going, once we have more fuel than we know what to do with, which I don't know when that's going to happen, there's going to be better uses for some of those neutrons, and I could see reprocessing high-level waste as a good use of that.
Yeah. Hold on just a second. Okay, so okay, last question. For those of us who are considering their career choices or coursework, what advice do you have? I mean, you've got this fabulous background. I mean, you know, the light bulb went off for you in high school, and you concentrated on MIT. You did this fabulous project in Europe as a freshman. I wish I had done that. And you got to where you want to be, and you obviously know your stuff and love it. You know, I mean, it's not
Oh, yeah.
work for you, is it? You just love what you're doing. What advice?
You know,
do
it's funny. I was just thinking this. I haven't taken more than 2 weeks off in a row since 2005, and it's because I haven't felt the need.
Yeah, you love what you're doing. That's so wonderful. What advice do you have for the rest?
Well, for everyone, I'd say, no matter what walk of life you're in and what you're thinking of doing, it's some advice that I was given while I was on the path to tenure, and I didn't understand it until I got there. It's if just do what you like to do and do it well, and you'll do great things. So when I was being asked these questions, what are you going to research, or what am I going to do with my life? What am I going to do with my group? In the end, as trivial as it may sound, if you do what you like, you'll probably get good at it, and it'll probably be valuable to a lot of other people. Now, that's not necessarily the fastest path to financial sustainability. And in some cases, that isn't a path to financial sustainability. If you love making a certain type of art that nobody else likes, you might not be able to sell much for a very long time. You might not be recognized till after you're dead, but you will do something great. And so, of course, I understand the need to balance short, medium, long-term financial needs, both yourself and anyone you're supporting. But I would say that a more likely path to that than I appreciated was to get really, really, really good at the things you like.
The nuclear field is exploding. We've got all this money going into it, both from government and from private industry and from the venture industry. And the enrollments at MIT are up as well.
Sure.
When I was there, we did not have an undergraduate program. You had to go major in something else, and then you could go into nuclear as a grad student. So in the enrollment, we got an undergrad program now, and the enrollments are way up. What for somebody who wants to get in that program or get into nuclear in general, where do you tell them to start? What would you say to them?
Yeah, I would say if you want a taste of it, if you just want to find out, is this something I want a little taste more of? And if you're not at MIT, we released a MOOC, a massive online open course.
Right.
That's like the first third of 2201, plus a smattering of fission, fusion, and security. We've had 16,000 people complete it to date in the first 4 years. Wow. And I'd love to see this hit the millions, because that's how we solve. Remember before you said what's wrong with nuclear in this country?
Right.
Education and literacy. You don't have to get a degree in it. You don't even have to finish a course in it. If more people just took a MOOC, an 8-week, a few hours a week MOOC, and became literate in the nuclear stuff, we would all be informed enough to debate the issues from a logical point of view without letting fear take over. But at the same time, not ignoring fear, right? I mean, to me, it took me a long time to learn this too, that emotions are just kind of your higher level intuition trying to get out, and they are not to be ignored. Oftentimes, They take longer to justify and understand than logic. Sometimes lead you down the right path. Sometimes you do have to trust your gut, but I've learned not to ignore it. So at the same time, I would want to see that focused through logic and common units and common debate and common respect, so that people don't fear nukes. People don't think there's anything evil about it. It's just another technology, and it's a weapon we have in the fight against climate change if we choose to use it.
Well, this has been, Mike, another drink out of a fire
Thanks.
into a teacup. It's just fabulous. You're just tremendous, and I want to thank you so much. Would you, could we do this again in a year, maybe sometime next year? Maybe
Absolutely.
we'll have version 2, and
I'd be happy to.
this would just be fabulous. Yeah. So, Doug, do you want to come back on?
Love to. So, Mike, I've been doing this for 12 years, and in the virtual now, we're in our 4th year. And I always look at attendance over at 15-minute increments.
Mhm.
And so when you held your audience for nearly an hour and a half,
Cool.
with a less than 10% reduction at the end, that's, I think, a record. So the other thing is you made our jobs, of course, much, much easier because, even Larry did his usual really great job with the Q&A. He didn't have to come up with as many of them as, because you already had that worked out in your presentation and going back and forth, with Q&A, which, by the way, fabulous job on that.
Thank you.
So you've kind of set a new standard for us, Mike, and I just want to tell you how much we appreciate it, because I was mostly able to just sit back and watch, which I really enjoyed, and learn more as a consequence. And I hope that our audience feels the same way, that they could do that and come away with a lot of really good insights, because I think they were there. So thank you so much for doing this. I will echo what Larry said. It would be great for us to figure out a way to bring you back again and do something maybe not exactly like this, but somewhat like this, because I believe the interest is going to be there. As I said at the very beginning, number of registrations was the second largest, second to Jacopo's earlier talk, and not by much, by the way. And the actual audience that you had was very close. So my great gratitude and applause for this. And we really appreciate what you've done for us tonight. And thank you so much. And with that,
My pleasure.
Go ahead and say what you want. Go ahead.
Thank you all for the great, for sticking around, for the great questions. I'm sorry I couldn't answer them all, but I'm easy to find. I am at mit.edu. So if anybody wants to send them along, I'd be happy to keep these up. And just to make sure, I just did a Control-A, Control-C, Control-V, and I think if this works, great. I think I just captured the entire Q&A.
Yeah.
Great.
Awesome.
I've got a backup for you in case you need it.
Yeah.
Okay.
Yeah.
Yeah. So I'll be happy to continue this with anyone who would like to.
Yeah, and just to go over your email address again, it's the 3 words, "Here I am," all is 7 letters combined, at mit.edu. So
I just sent it in the chat. Yeah.
oh yeah, there you go. Yeah. Okay.
Well, this is great. So everybody who joined and still on, thank you so much for doing it. And we hope we can duplicate something like this again in the near future. So good
Yeah,
evening,
and
everybody.
Thanks y'all for having me. I like you asked, I'll be happy to do this again in a year.
Great.
And go Warriors.
Go Celtics.
Go
thank
go Celtics. Yeah.
All right. Thanks, everyone.
That's it. Thank you.